Find the open intervals on which the function is increasing or decreasing. The function is f of x equals x to the 2/3 power times the quantity 16 minus x squared. In order to find the open intervals where f of x is increasing or decreasing, we must find the critical values of f of x. To do that, you need to find f prime of x. It looks like we will need to use the product rule for this derivative. However, I'm going to distribute this x to the negative 2/3 power to each term to make finding the derivative much easier. This is 16 times x to the 2/3 power minus x to the 8/3 power. So now instead of using the product rule, I can use the power rule to find the derivative. F prime of x will be 16 times 2/3 x to the negative 1/3 power minus 8/3 x to the positive 5/3 power. To simplify this down a little bit, the derivative will equal 32 over 3x to the 1/3 power. The x to the negative power gets moved to the bottom. 16 times 2 is the 32. And from that, we will subtract 8 over 3 x to the 5/3 power. This derivative is as simple as it gets. And now I can set it equal to 0 and solve for x, as well as look for any undefined values of the derivative. So 32 equals 3x to the 1/3 power minus 8/3 x to the 5/3 power equals 0. I can see that the derivative has an x in the denominator right there. And if you set that denominator equal to 0 and solve for x, you will see that the derivative is undefined at x equals 0. So this is already one critical value for the derivative. As we go through and solve this equation for x, I will need to multiply all terms by 3x to the 1/3 power, and that'll just make life a heck of a lot easier. When I multiply that to this first term, it will cancel out the denominator. When I multiply this to the second term, it will cancel out the 3 and leave us with a multiply x to the 1/3 power. And when I do this to the right side of the equation, it still leaves us with 0. So on the left side, it'll be 32 minus 8. And up here, x to the 5/3 power times x to the 1/3 power will equal x squared. From here, we can add 8x squared to both sides, so 32 equals 8x squared. You can divide both sides by 8 to get 4 equals x squared. And finally, when you square root both sides, you get x equals plus or minus 2. And these are more critical values for the derivative. So all in all, we have 3 critical values: x equals 0 and x equals plus or minus 2. In order to find where the original function is increasing or decreasing, I needed these critical values, so I plotted them on my number line. And these critical values are going to divvy up the number line into different intervals. So we will have an interval that goes from negative infinity all the way over to negative 2. We will have another interval going from negative 2 to 0, another one from 0 to 2, and another one from 2 all the way over to infinity. So how can we tell? We need to pick some test values. I will use -8, I will use -1, I will use +1, and I will also use +8. And you might be wondering, why did I pick these particular values? Well, in the derivative, this 1/3 power and this 5/3 power, at some point we are going to be taking the cube root of a number. -8 is easily cube rooted. -1, +1, +8, they're all easily cube rooted. So we need to take all of these test values and evaluate the derivative at every last one of them. So f prime of -8, f prime of -1, and so on. So f prime of -8 looks something like this. 32 over 3 times -8 to the 1/3 power minus 8/3 times -8 to the 5/3 power, which reduces to 32 over 3 times -2 minus 8/3 times the cube root of -8 is -2, and then we still need to raise that to the 5th power. So getting rid of the 3 in the denominator in this exponent makes the -8 turn into a -2, but we still have that 5th power. Simplifying even further, you can see that we will have 32 over -6 minus 8 times -32 all over 3. Even more, we have -16 over 3, and here in this last one we have a negative times a negative will give us a positive. 256 over 3. At this point I can say for sure that this is bigger than 0. And since the derivative is bigger than 0, the original function is increasing on that interval. If you go through and do similar work, like this down here, for when x equals -1, +1, and +8, you will see that you'll get intervals that are less than 0, or the derivative will be less than 0 between -2 and 0. The derivative is bigger than 0, and the derivative over here is less than 0. And that tells you that the original function will be decreasing, increasing, and decreasing on those intervals. So down here in the lower left, increasing, the original function is increasing from -infinity until -2. On the next interval here, the original function is decreasing. So it is decreasing from -2 until 0. And then after that, it is increasing again, so I have to union this interval at the end of it from 0 to 2. And then after that, I union this, that it is decreasing from 2 to infinity. Here are the intervals on which the original function is increasing or decreasing. On this last slide, we will analyze what the intervals of increasing and decreasing can tell us about the original function. The first derivative test states if a function stops increasing and starts decreasing, then there is a relative maximum at that x value. So similarly, over here, there's another relative maximum. And the first derivative test states that if a function stops decreasing and starts increasing, then there is a relative minimum at that x value. Now, in order to find the ordered pair of where the relative max and relative min take place, you need to substitute the x value back into the original function. So we'll find f of -2, which is -2 to the 2/3 power times 16 minus -2 squared. What that leaves you with is the cube root of 4 times, this is 16 minus 4 is 12. And if we just rewrite that a little bit, that says 12 cube root of 4. So when we put in an x value of -2, the function gave us back a y value of 12 cube root of 4. So this is one relative max, -2 comma 12 cube root of 4. If you repeat this procedure by substituting in 0 for the relative minimum, you will see that the relative minimum coordinate pair will be 0, 0, and the coordinate of the relative max on the right side will be 2 comma 12 cube root of 4. So there are 3 relative extrema, and they are all listed